So for standard 7.1, I'll be doing a problem from the book 7.29, and it asks us to figure out the motion of the angle of this angle as time passes by if this whole system or if this pendulum is located on a circular path which is moving with angular velocity w. So we have to figure out what is the position of the angle as time passes by for this whole system. So the first thing that I realize is that the final position of the pendulum, or the end of the pendulum, is equal to the vector addition of the radius and the length. So if I figure out where these two are in terms of x and y, I'll figure out the final position of that. So that's where our resultant vector is. That's why it's just the addition of these two. So I'm going to use Lagrange's equation to figure out this question. And from Lagrange's equation, we know that it's equal to kinetic energy minus potential energy, where kinetic energy can be rewritten as this, where r hat dot is just a derivative of this resultant vector. So we have to figuring out the resultant vector, it's just the addition of r1 and r2, and adding those two, you get this equation, and then once you realize, or what I realize is that the angular velocity can be rewritten as angle over time, and then I can just rearrange the equation to give me that the angle is equal to a wt. So moving on from then, I just rewrite wherever I see the angle, I just rewrite it as wt within each term. And so one thing I made sure I did was that when I was adding the r1 and r2, I just made sure that my x's were adding up together and my y's were adding up together, so I didn't get that mixed up. So once I have that equation, I just derive it with respect to time, and this is the equation that you will get once you do that. And once I have that equation, I want to square it, have the absolute square of that, because that's how that velocity looks like. So I'm trying to make it look like that. So this is what it looks like once you square it. And then if you do the algebra behind it, you should be left with this equation over here. And therefore, that means my kinetic energy is equal to this equation right over there. And my next step is to figure out what is the potential energy. Now, potential energy is slightly easier, where potential energy is equal to mg times the height, where the height is determined by the y direction. And we already know what the L contributes in the y direction and the R contributes in the x, or the R2 vector and R1 vector, how much they contribute in the y direction. And that's how much they do, and then you can rewrite this equation as that's the potential energy. Now the addition of those two equations gives me the Lagrange's equation as that. So the next step is to solve this. Now, solving this, you're going to use one of the properties of Lagrange's equation is that you can, if you do this to it, it's equal to 0. So that's what we're going to do right now. So the first thing to do is to figure out this part over here. And to do that, you just derive the Lagrange's equation. So from Lagrange's equation, if I were to derive that with respect to the angle of the pendulum, I just find all the terms that have it. So this term has a pendulum, and this term has the angle and angle. So the other terms will just fall off, and that's why I'm left with this final equation over here at the bottom. And to derive the Lagrange's equation in terms of the angular of the pendulum dotted once,